To accurately quantify how a continuous field penetrates a specific region of space, we have to establish a rigorous method of measurement. Physics solves this spatial measurement problem by borrowing the concept of flux directly from fluid dynamics. This diagram illustrates fluid flux, measuring the exact volume of liquid crossing a flat surface over time. The calculation requires two mathematical inputs: the liquid's velocity vector, labeled v, and the planar area it crosses, labeled ds. In fluid dynamics, flux strictly measures the observable physical movement of matter passing from one side of a boundary to the other. We analyze electric fields using an analogous system, but we immediately encounter a physical contradiction. This model shows a uniform electric field piercing a planar surface. Unlike water, an electric field is static. It does not physically flow, and it does not move matter. The field lines pierce the plane, but nothing is actually crossing the threshold over time. To calculate electric flux, we discard the concept of physical flow. Instead, we build a purely geometric mathematical model. Electric flux quantifies the degree to which a field penetrates a given boundary, relying entirely on spatial orientation rather than the movement of mass. In everyday geometry, we treat area as a simple scalar magnitude, like square meters. But when calculating field interactions, a scalar value is insufficient. The exact number of field lines intercepted by a surface depends entirely on how that surface is oriented in space. The mathematical solution requires treating area as a vector with magnitude and direction. We specify its direction by its normal, the axis perpendicular to the plane. As the plane tilts, the normal vector rigidly moves with it, maintaining a 90-degree angle. Without defining area as a rigidly oriented vector, mathematically determining the penetration of a directional field is impossible. Here, we place our newly defined area vector, delta S, inside the uniform electric field, E. When perfectly perpendicular, the angle theta is 0 degrees, and maximum field lines cross the surface. If we rotate the plane 90 degrees parallel to the field, theta is 90 degrees, and 0 field lines cross. At an arbitrary tilt, the effective intercepting area shrinks. The geometric projection of this effective area is exactly delta S multiplied by the cosine of theta. Electric flux, delta phi, is proportional to the field magnitude multiplied by this projected area, giving us E times delta S cosine theta. This formulation perfectly matches the exact mathematical definition of a vector dot product, E dot delta S. Keep in mind a rigorous physics caveat. Drawing discrete field lines is merely a visual abstraction. The physical quantity of flux does not literally equal a count of lines. The dot product acts as a perfect geometric filter, mathematically stripping away any component of the field that does not directly penetrate the surface. Expanding this model from flat planes to closed three-dimensional shapes introduces a new geometric problem. This diagram of a closed shape highlights the inherent ambiguity of the normal vector. A flat surface patch technically has two perpendicular directions, one pointing inward and one pointing outward. For mathematical calculations, we must determine the true direction. Physics resolves this with an absolute convention. For any closed surface, the area vector always points in the direction of the outward normal. Universally adopting this outward normal convention ensures consistent signs when calculating the net flux for an entire volume. This leads to our final geometric question. How do we calculate flux for a continuously curved surface, where the electric field and the normal vector are constantly changing direction? This demonstrates discretization. We fracture the complex, smooth curve into dozens of discrete flat planar patches, delta S. Treating each infinitesimally small patch as a perfect plane, we assign a unique outward normal vector. Total flux is simply the summation of these dot products. This grid allows us to process a continuously varying surface as a collection of standard vector dot products. But as long as the patches have a finite size, the calculation remains only an approximation. To correct this, we apply the fundamental limit of calculus, taking the size of the area elements infinitely close to 0. At this exact limit, the discrete approximation becomes mathematically exact. The summation notation formally transforms into the integral sign. We define this final equation as the continuous surface integral of the electric field over an area. Derived strictly from this calculation, the official units of electric flux are newtons per coulomb times meters squared.
By vectorizing area and pushing geometry to its calculus limit,